Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
My laborious Taylor's expansions of 1981 were how I approximated the value of each of my solutions by taking the sum of its derivatives at a given point. If Taylor's expansions yielded my a priori error estimates that I used to pre-select the most hopefully accurate finite difference algebraic approximations of the 9 partial differential equations called Philip Emeagwali's equations that I invented, I contributed to mathematical knowledge, and my contribution to algebra and calculus was the cover story of top mathematics publications such as the June 1990 issue of the SIAM News. One fact that I never mentioned before was that I often pursued false mathematical trails. Back in 1981, I was unreasonably obsessed with the Hopscotch algorithms as a numerical solution of partial differential equations. I was obsessed with Hopscotch methods because I was unreasonably optimistic and believed that Hopscotch methods are hybrid explicit implicit methods that could be very accurate, and that Hopscotch methods could enable me to email my initial boundary value problems and email them across a new internet that I visualized as a new global network of 65,536 commodity off-the-shelf processors. After a year of seemingly endless mathematical analysis of Hopscotch algorithms and computational experiments of Hopscotch computational fluid dynamics codes, I discovered that I was following a false trail and that Hopscotch algorithms were overhyped. After wasting extraordinary amount of time, I resettled on explicit finite difference approximations. In the end, I invented explicit finite difference algebraic approximations of the 9 partial differential equations called Philip Emeagwali's equations that I contributed to modern calculus. That was how I scribbled new calculus that had never been scribbled on any blackboard before. That was how I coded new algebra that had never been coded by any computational algebraist before. That was how I saw a new supercomputer that had never been seen by any supercomputer scientist before. It's often said that parallel processing across millions upon millions of tightly coupled commodity off-the-shelf processors that shares nothing with each other is the biggest advance in computing since the programmable computer was invented back in 1946. In my country of birth, Nigeria, a million billion trillion floating point arithmetical computations are massively parallel processed each day and massively parallel processed to discover and recover the otherwise elusive crude oil and natural gas that are buried a mile deep in the Niger Delta oil fields of Nigeria. As a discoverer hopeful back in 1974 in Corvallis, Oregon, United States, I asked a big question that had never been answered before. That overarching question was, how do we parallel process across a new internet that is a new global network of 64 binary thousand computers? If that big question that I asked in 1974 was already answered, or if parallel processing was already discovered, my invention of the massively parallel processing supercomputer would not have been cover stories and would not have been recorded in the June 20, 1990 issue of the Wall Street Journal. If the answer to that big overarching question was known, I would not have gotten telephone calls from the likes of Steve Jobs, who wanted to know how I invented the massively parallel processing supercomputer that is faster than the vector processing supercomputer. Steve Jobs wanted to know how I recorded 3.1 billion calculations per second. As an aside, my invention of parallel processing that occurred on the 4th of July 1989 inspired Steve Jobs to use 4 processors that processed in parallel to also attain a speed of 3.1 billion calculations per second and record that speed in his first Apple personal supercomputers called the Power Mac G4. Steve Jobs introduced his personal supercomputer at the Seymour Seabolt conference that took place in San Francisco on August 31, 1999. Like the modern supercomputer, the fastest speed in your computer, are coming from parallel processing. The new supercomputer knowledge that made the news headlines was that I, Philip Emeagwali, had invented how to massively parallel process, and that I invented the technology that drives the modern supercomputer and invented the technology on the 4th of July, 1989, and invented the technology in Los Alamos, New Mexico, United States. I invented the parallel processing supercomputer technology to enable me to solve the toughest problems arising in extreme scale algebra. Such mathematical physics problems arise when trying to discover and recover crude oil and natural gas, and do so from the Niger Delta oil fields of my country of birth, Nigeria. My quest for the new algebra, that is my contribution to algebra, began with the arithmetic times table that I memorized in 1960 in first grade at St. Patrick's Primary School, Sapele, in the then western region of the then British West African colony of Nigeria. That times table went to only 12 times 12. That times table was near the beginning of knowledge of arithmetic. On the 4th of July, 1989, in Los Alamos, New Mexico, United States, I, Philip Emeagwali, mathematically invented how to massively parallel process arithmetic times tables and parallel process them across a new internet that is a new global network of processors. I invented new algorithms or new instructions that told each processor what to compute within itself and what to communicate to its up to 16 nearest neighboring processors. Since the first programmable supercomputer was invented in 1946, each supercomputer manufactured was faithful to its primary mission, namely, to solve the most extreme scale problems arising in computational physics and to increase productivity, reduce time to solution, and reduce time to market. Supercomputing is mathematics intensive. For that reason, most supercomputer scientists are, in part, research computational mathematicians. In supercomputing and in computational physics, to discover is to make the impossible to solve possible to solve. The first person or the discoverer makes the impossible possible, and thereafter everybody knows that parallel processing is no longer a waste of everybody's time. I, Philip Emeagwali, was credited for making the invention of massively parallel processing, the technology that makes supercomputers fastest. I invented parallel processing when the supercomputer technology was scorned, ridiculed, and rejected by the likes of Steve Jobs. I invented parallel processing when the supercomputer technology was presumed to be untestable and even wrong. My discovery that the impossible to solve, arising in extreme scale algebraic computations, is possible to solve across a new internet that is a new supercomputer and a new computer was recorded in the June 20, 1990 issue of the Wall Street Journal. I'm Philip Emeagwali at emeagwali.com. Thank you.
Insightful and brilliant lecture.